Okay. Okay, welcome back for this second part. So here, if you recall, the amplitude response from the previous recitations, the amplitude is governed by 1 over the characteristic polynomial evaluated at I omega. Where does I omega come from? If you recall, it comes from the exponential response formula, because on the right-hand side here, we have a cosine omega t that is, then we complexify exponential I omega t, etc., to get the amplitude response. So the amplitude is going to be the largest for basically values of I omega that are the closest to the poles of the polynomial, to the poles of this function. Right. Basically, the poles of the 1 over characteristic polynomial is going to give us the 1 over 0, which will give an amplitude response that goes to infinity, so the largest response. So we want to choose our frequency I omega. Basically, we want to look at this diagram and look at the poles that are the closest to the values that are going to give us P of s equals to 0. And this is basically a diagram that gives us the pole of this 1 over P. And so we want to choose a value for I omega, which will be on the imaginary axis, that is the closest to one of these two poles. Given that we work with positive frequencies, we would want, for example, to choose I omega equals I4. Okay, so it would be here, or just omega equals to 4. And this value of omega would get us very close to this pole, which would mean then that we are 1 over a very small number, which means that the amplitude response will be the biggest. So that's the idea behind the resonance and looking at, again, the phenomenon of resonance from the pole diagram perspective and with the idea of the use of the Laplace transform behind the whole technique. So that ends the session. And the goal was really to learn to interpret the meaning of the poles in the pole diagrams and how do the poles give us an idea, an insight on the behavior of the system on the long term.